Welcome back to our channel, and on our today's lesson we are going to plot the bending moment diagram as well as the shear force diagram for this continuous beam that is supported on 4 supports, that is support A, B, C as well as D. It is loaded with 2-point loads. At point E we have a point load of 80 kilonewtons, point F a point load of 50 kilonewtons. Between C and D, we have a UDL of 10 kilonewtons per meter. And we are going to begin with determination of the maximum bending moments at each span. For span AB, we are going to determine the maximum bending moment at point E due to this 80 kilonewtons rod. Between span BC, bending moment at F because of this 50 kilonewtons point rod, and at span CD we are going to determine the maximum bending moment due to this UDL of 10 kilonewtons per meter. And we are going to begin with the span AB. So ladies and gentlemen, join me so as we learn how to plot the bending moment as well as the shear force diagram. And if you are here and you are here to subscribe, please consider subscribing to this channel for more and more structural engineering calculations. Good, so we are going to begin with the span AB. Therefore, we go to the span A to B. And for the span AB, the bending moment at E, that is bending moment at this point E, will be given by W1, A1, B1 divided by L1. And in this case, W1 is the 80 kilonewtons point rod, A1 is this 2 meters, B1 is this 3 meters, and L1 is the span A to B. And in this case, W1 is 80 kilonewtons, A1 is 2 meters, B1 is 3 meters, and L1 is 5 meters. And that's going to give us a bending moment of 96 kilonewtons meter. From there, we go to the span BC. Therefore, for span B to C, the bending moment at F, which in this case is the maximum bending moment between B and C, will be given by W2, A2, B2, W2, A2, B2 divided by L2, which in this case will be given by W2 is this point rod of 50 kilonewtons, A2 is the 4 meters span, B2 is this 3 meters, and L2 is 7 meters, that is between the span B to C. And this is going to give us a bending moment of 85.71 kilonewton meter. So that is the bending moment at F. Finally, we go to the span CD, and therefore for the span C to D, the maximum bending moment will be given by WL3 squared divided by 8, since that span is loaded with a uniformly distributed load. And this is going to be a UDL of 10 kilonewtons per meter multiplied by the square of 8 meters, divide this by 8. And this is going to give us a maximum bending moment of 80 kilonewton meter. So those are the bending moments at each of the 3 spans that we have. From there, we are going to plot the bending moment diagram due to these 3 bending moments that have been caused by the loads between those spans. And we are going to begin with bending moment at E, which is 96. So yeah, let's approximate it to be at that point. Then we join this to that point. Good. And let's try to make this line to be as straight as possible. Yeah, that's a perfect straight line. So this is 96 kilonewton meter. The bending moment at F, 85.71. So 85.71, approximately there. So another straight line all the way to B, pop, up that point. And then we join it to C. Let's see what we are going to have. Oh no, we didn't just do that. Let's see. Let's try another. One more time. We need a straight line joining it to C. Oh, perfect. That one is now great. So this is a bending moment of 85.71 kilonewton meter. Then we have a maximum bending moment here of 80 kilonewtons meter. This one should be a smooth curve since the span is loaded with a UDL. Oh man, did we just do that? Let's see. 8 there. Oh good. That must be a smooth curve now. So this is 80 kilonewton meter. Perfect. From there, we are going to determine the area of each bending moment diagram together with its center of gravity from these points. Point A, B, C, D. Okay. So we go to the span AB. So we are going to begin with span AB. And now, for span AB, we need A1. That is the area of this triangular shaped bending moment diagram, which will be given by a half of the base. The base is 5 meters and the height is 96 units. And that is going to give us an area of 240 square meters. Then we need the center of gravity of this bending moment diagram, distance of the center of gravity of this bending moment diagram from the end A. And by x1, let's call it by x1, that's going to be given by L1 plus A1 we divide by 3. That's the formula, and this is going to be equal to L1 is 5 meters, A1, that is the distance from E to A, 2 meters, and then we divide that by 3. So that is 7 divided by 3, which is 2.3333 recurring, 2.33 meters. Awesome. Then from there we go to the span B to C. So for the span BC, likewise, the area of that bending moment diagram, that is A2 in this case, will be given by a half of its base, which is 7 meters, multiplied by its perpendicular height, which is 85.71 units. And that's going to give us an area of 300 square meters. We need bar x2. And by x2 in this case, we are going to begin with by x2 with point C being the origin. With point C being the origin. That is center of gravity, distance of center of gravity of this bending moment diagram from the center of gravity all the way to C. So in this case, C being the what? Being the reference. So or being the origin in other words. So x by x2 will be given by L2 plus, so with C being the origin, we are going to have B2. So we have L2 plus B2, then we divide this by 3. And this is going to be 7 plus B, which is 3 meters. Then we divide this by 3. So that is definitely 10 divided by 3, which is 3.333 recurring. So 3.333 meters. So that is C being the origin. Then we need bar x2 with B being the origin, with B being the origin. So in this case, we are going to have this bar x2. The second bar x2 will be given by L2 plus A2 divided by 3. So in this case, with B as the origin, we are going to use this A2 because B is the origin in the second case. So this will be 7 plus 4 meters, which is the value of A2. We divide this by 3. And I know that is 11 divided by 3, which is 3.666666 recurring. So that is 3.667 meters. Very good. So we are remaining with the last span, which is the span C to D. So for span C to D, the area, that is A3, area of this bending moment diagram will be given by this formula: 2/3 of its base, which is 8 meters, multiplied by its perpendicular height, which is 80 units. And that's going to give us an area of 426.6667. 426.667 square meters. So that is the area of that smooth curve. Bar x3. Bar x3 will be the distance from the center of gravity of this bending moment diagram, which is a smooth curve, all the way to the end D. So that is bar x3. And it will be given by half the span C to D. So by x3, that is half of 8 meters, which is 4 meters. Very good. So after we are done with all that, the next operation will be application of the 3-moment theorem. So we go to application of the 3-moment theorem. Or we can also call it application of the CLAPEYRON'S equation of 3-moment, or application of the 3-moment equation. Any can do. Our formula is going to be like this: MAL1 plus 2MB into bracket L1 plus L2 plus MCL2 will be equal to 6A1 bar x1 divided by L1 plus 6A2 bar x2 divided by L2. Good. Since the beam is simply supported at the end A, the bending moment at A is going to be 0. And therefore, we are going to remain with this 2mb into bracket L1, which is 5 meters, plus L2, which is 7 meters, plus L2, 7 multiplied by MC, being equal to 6 times A1 is 240 square meters, by X1 is 2.33 meters, so we multiply that by 2.33 meters, then we divide by L1, which is 5 meters, plus 6 multiplied by A2, 300 times bar X2, in this case bar X2 with C being the origin, yep, C being the origin, and that is 3.3333, C being the origin, so we have 3.333 recurring, we divide by L2, which is 7 meters, so we have 24 mb plus 7 mc being equal to 6 times 240 times 2.33 divided by 5, that is 672, plus the other part will give us 857, and this is going to lead us to this 24 mb plus 7 mc being equal to, when we add these two, they are going to give us 1529. Then we can simplify this equation by dividing through by 7. So we divide everything by 7, and when we do that, 24 divided by 7, that is 3.43 mb plus mc being equal to 1529 divided by 7, that is 218.43. And let's make MC the subject. And when we make MC the subject, we are going to have MC being equal to 218.43 minus 3.43 mb, and we are going to call that equation 1. We are going to substitute the value of MC somewhere in our next span. Then we go to the spans. So for spans B, C and CD, for the spans BC and CD. So in this case, with the CLAPEYRON'S equation of 3 moments, you must work with 2 spans at a time. So we are going to have this formula, MBL2, because we are dealing with the span BC and CD. Therefore, MB times L2 plus 2MC bending moment at C into bracket L2 plus L3 plus MBL3 is equal to 6A2 bar X2 divided by L2 plus 6A3 bar X3 divided by L3. That will be our formula for the next 2 spans. And in this case, the beam at the support D, that is the bending moment at the support D, is going to be 0. Therefore, MD is equals 0. So we are going to remain with MBL2, and in this case L2 is 7 meters. Therefore we have 7 MB plus 2MC into bracket L2, which is 7, plus L3, which is 8 meters, is equals to, since that is 0, 6 times A2, and in this case A2 is 300 square meters, 300 square meters times by x2. And in this case, by x2 we are using here is B being the origin. That is this point here being the origin. Okay? And by x2 B being the origin is 3.667. So we multiply by 3.667. Then we divide this by L2, which is 7 meters, plus 6 multiplied by A3, which is A3 is up here, 426.667 square meters, times by x3, which is 4 meters. Then we divide this by the span C to D, which is 8 meters. And this is going to give us 7 MB plus 7 plus 8, that is 15. 15 times 2, that is 30. So 30 MC, which will be equal to, when we solve this, that is going to give us 942.855. 942.855 plus the other part is going to give us 1280. So we add 1280. This is going to lead us to 7 MB plus 30 MC is equals to, when we add the two, they are going to give us 22.9. Very good. So this being our second equation, we have the value of MC in our equation 1, sorry. In our equation 1. So we are going to substitute this MC with this equation that we got as our equation 1. So this is going to be 7 MB plus 30 into brackets 218.43, 218.43 minus 3.43 MB, 3.43 MB. That will be equal to 22.9, 22.9. And this is going to be 7 MB plus, when you open this bracket, that times 218.43, that is 6552. 6552.9. 0.9 minus 30 times 3.43, that is 102.9. So minus 102.9 MB is equal to 22.9. Good. Then from there, we are going to have 7 MB minus 102.9 MB, which in this case is going to be equal to minus 95.9. Therefore, minus 95.9 MB plus 6552.9 will be equal to 22.9. This is going to be minus 95.9 MB being equal to, we take 6552 the other side of the equal side, this is going to be 22.9 minus 6552.9. We are going to have minus 95 MB being equal to negative 4330. Negative 4330. So to get the value of MB, we are going to divide both sides by negative 95. Negative 95. And the value of MB will be equal to 45.15 kilonewton meter. Kilonewtons meter. Very good. So that is the value of MB. Now, the value of MC will be 218.43 minus 3.43 MB. First of all, 3.43 MB, that is 3.43 times MB, which is 45.15. And that is equivalent to 154.87. 154.87. Good. So the bending moment at C, let me write it down here. Bending moment at C will be given by 218.43, 218.43 minus 154.87. 154.87. So that's going to give us a bending moment at C, bending moment of 63.56 kilonewtons meter. Therefore, we have the bending moment at B as well as the bending moment at C. Very good. After getting the values of the bending moments at B as well as bending moment at C, we are going to plot those bending moment diagrams at B, at support B, as well as at support C. And we are going to have this bending moment at B, 45.15. So 45, approximately half of 80, just above half of 80. That's so high. About that pointer. So we are going to join A2. The bending moment at A is 0. So we are beginning from 0 to bending moment at B, which is 45.15 kilonewtons meter. Then we have the bending moment at C, which is 63.56, just some few units below 8 there, so about that point. So I'm going to join 45 to that 63.56 kilonewtons meter. Then the bending moment at D is 0, so we join 63.56 to 0 bending moment at D. So that is our perfect bending moment diagram. And then from there, we are going to shade off the outline of our bending moments diagram so that they become very clear. Good. So after shading the outline of our bending moment diagram, we are going to write this as positive bending moment. Here we have a negative bending moment. This is going to be a positive bending moment. This one is a negative bending moment. And finally, this one is a positive bending moment. The bending moment at support B is negative because when our beam bends, it is going to sag between AB, which is positive, and at B and C, it is going to hug, which is a negative bending moment. Very good. After plotting the bending moment diagram, we are remaining with plotting the shear force diagram. And for us to plot the shear force diagram, we need to calculate the shear forces. And for us to be able to calculate the shear forces, the first thing we are going to do is to calculate the values of these reactions at these four supports. Reaction at A, at B, at C, as well as reaction at B. And we are going to go to reactions, calculations. Yep. Reaction calculations. And in this case, we are going to begin with taking moments. Taking moments about C from D. So we are going to take moments about C from the end D. And this is going to give us reaction at D multiplied by the distance from D to C, which is 8 meters. That is an anti-clockwise moment, plus the bending moment at C, which is 63.56 kilonewtons meter. 63.56 kilonewton meter is equals to, between D and C, we have a UDL of 10 kilonewtons per meter. We convert it to point rod by multiplying it by the span 8, which will act at the mid span of the span C and D, which in this case is 8 divided by 2. And this is going to be LD times 8 being equal to, this is going to be, that is 320. So 320 minus, take 63.56, the other side of the equal sign. And this is going to be LD will be 256.44. 256.44 we divide by 8. And when we do so, we are going to get a reaction at D of 32 kilonewtons. Reaction at D, 32 kilonewtons. Very good. Then we go to calculation of the reaction at A. And in this case, we are going to take moments about B. Therefore, taking moments about B from A. So about B from A, we are going to have this reaction at A times the distance from A to B, which is 5 meters, plus the reaction, the bending moment at B, which is 45.15. So we add 45.15. That's going to be equal to the point rod at E, which is 80 kilonewtons, times the distance from E to B, which is 3 meters. Therefore, that is 80 times 3 meters. Therefore, clockwise moments being equal to anti-clockwise moments. So this is going to be RA times 5 being equal to 240, that is 80 times 3 minus 45.15. And the reaction at A will be given by 194, that is 240 minus 45.15, that is 194.85. We divide that by 5. And when we do so, that is going to give us a reaction of 39 kilonewtons, approximately 39 kilonewtons, since it is 38.9 something. Good. From there, we go to calculation of the reaction at B, and in this case, we are going to take moments about C. Therefore, we go to taking moments about C all the way from the end A. We are going to have this RA times the distance from A to C, which is 12 meters. Therefore, RA times 12 plus RB times the distance from B to C, which is 7 meters. Therefore, RB times 7 plus the bending moment at C, which is 63.56. These are clockwise moments in this case. 63.56 is equal to the following anti-clockwise moments. We have 80 times the distance from E to C, which is 3 plus 7, that is 10 meters. Therefore, 80 times 10 plus, at F we have 50 kilonewtons times the distance from F to C, which is 3 meters. Therefore, plus 50 times 3. And this is going to give us a reaction at A. We have it as 39 kilonewtons. Therefore, that is 39 times 12 plus RB times 7 plus 63.56 being equal to 80 times 10, that is 800, plus 50 times 3, that is 150. So 39 times 12, that is 467.64 plus RB times 7 plus 63.56 being equal to 950. That is 800 plus 150. Now 467.64 plus 63.56, that is 531.2. So we are going to have this RB times 7 is equals 950 minus 531.2, because 467.64 plus 63.56 is 531.2, and this is going to give us reaction at B of 950 minus 531.2, that is 418.8. So 418.8, then we divide that by 7, and this is going to give us a reaction at B, reaction of 60 kilonewtons, approximately 60 kilonewtons. Very good. So we have reaction at A, reaction at B, and reaction at D. We are remaining with the reaction at C, and in this case we are going to say this: the sum of all the upward acting forces, that is RA plus RB plus RC plus RD, is equals to the sum of all the downward acting forces, which are 80 kilonewtons plus 50 kilonewtons plus the UDL between C and D, which is 10 kilonewtons per meter, converted to point rod, multiplied by the span over which it is distributed. So we have the reaction at A being 39 kilonewtons, reaction at B being 60 kilonewtons, reaction at C, that's what we are calculating, plus reaction at D, which is 32 kilonewtons. That is going to be 80 plus 50. 80 plus 50, that is 130. 130 plus 80, that is 210. So is equals 210. And the reaction at C will be given by 210 minus 39 plus 60 plus 32, that is 131. And this is going to give us a reaction at C, reaction of 79 kilonewtons. So we have 79 kilonewtons being the reaction at C. Good. So we can write those reactions on our loaded diagram. We have RA being 39 kilonewtons. We have RB being 60 kilonewtons. So we have 60 kilonewtons. RC 79 kilonewtons. And finally RD, we have 32 kilonewtons. Very good. Now, after we are done with the calculation of the reactions, finally we are going to calculate the shear forces, so that we use those shear forces to plot the shear force diagram, that is, to plot the SFD. Good. So we go to shear force calculations, and in this case we are going to begin with the shear force at D. So the shear force at D is going to be equal to the reaction at D, which is 32 kilonewtons. Then from there we go to shear force between D and C, because of this UDL, uniformly distributed load, which is going to be 32, that is the shear force at D, minus the point rod between D and C, which is this 10 kilonewtons per meter UDL multiplied by 8, which is 80, converting it to point rod. So 32 minus 80. and that 2 minus 80 is minus 48, negative 48 kilonewtons. Then from there we go to shear force between C and F. Between C and F, which is going to be this minus 48 kilonewtons. We add the reaction at C, which is 79 kilonewtons, and that is going to give us a shear force of 31 kilonewtons. So we have 31 kN, 31 kilonewtons. Then from there you go to shear force between F and B. Shear force between F and B. That is going to be 31 kilonewtons. That is this shear force between C and F. We subtract the point load at F, which is 50 kilonewtons. So 31 minus 50. And that 1 minus 50, that is negative 19 kilonewtons. So that is the shear force between F and B, or B and F, any kind of, between F and B. Very good. Then we go to shear force between B and E. So shear force between B and E, that will be given by the shear force between F and B, which is negative 19 kilonewtons, plus the reaction at B, which is 60 kilonewtons. So we add 60 kilonewtons, and that is going to give us 41 kilonewtons. 41 kilonewtons being the shear force between B and E. Then we go to shear force between E and A. E and A, which will be given by this shear force between B and E, 41 kilonewtons. We subtract the point load at E, which is 80 kilonewtons. So 41 minus 80, that is going to be minus 39 kilonewtons. And finally, the shear force at A, it is going to be equal to the shear force between E and A, which is negative 39 kilonewtons. Very good. So, ladies and gentlemen, that is how we calculate the value of the shear forces. Then we are going to use those shear force calculations to plot the shear force diagram. Starting with the shear force at D, which is 32 kilonewtons. Let's approximate it to be here. So that is 32 kilonewtons. So we write there 32 kN. Then we go to shear force between D and C. It is going to change uniformly from 32 kilonewtons to negative 48 kilonewtons. Negative shear forces will appear below this line. So negative 48, let me approximate it to be there. So that is a uniform change exactly at the required point. So that is 48 kilonewtons. Then we connect that to the horizontal line. Shear force between C and F, that is 31 kilonewtons. So 31 just below 32. Yep. So that is how it's going to be. Connect it down there. So this is, and then we also connect this point to the horizontal line. So this is 31 kilonewtons. Then from there we go to shear force between F and B. Between F and B we have negative 19. So below this line, negative 19 will be there. So this is where we have negative 19. We connect it to B and then to the horizontal line. Good. So this is 19 kilonewtons. Then the shear force between B and E, 41 kilonewtons. So definitely above 31. So that's where it's going to be. So this is 41 kilonewtons. Then connect that to the horizontal line. Take it to the horizontal line. shear force between E and A, that is negative 39. So negative 39, yep, definitely above 48 there and below 19. So let me approximate it to be there. Then we connect it. Then finally shear force at A, 39. So we have 39 kilonewtons. That is negative shear force, negative, negative. Negative shear forces appearing below this horizontal line. Positive shear forces appearing above this line. Well, so that is our shear force diagram, ladies and gentlemen. Then, to complete it, we shade off its outlines. Yep, so ladies and gentlemen, that's how we plot a bending moment diagram as well as a shear force diagram for such a continuous beam. So we thank you so very much for watching our video, and if you have liked it, please consider subscribing and don't forget to hit the notification bell so that every time we record and upload a new video, you will be the first person to be notified. Thank you very much. Yep.